In this video, we will look at how to generate packing patterns in Mobius. We will use a flat grid data structure for generating a set of close-packed hexagons. A nested loop is used to move through the grid positions using two range functions. At specific locations, a hexagon will be generated. Two local functions are defined. The first function creates a hexagon at a particular location in the grid. The input parameters for the function are the list of positions, the width of the grid in the x direction, and the start index. The start index is a flat index that specifies the location to generate the hexagon. It is the bottom left-hand corner of the shape. Based on the start index, 6 positions are extracted from the grid and returned. The second function fills the grid with hexagons. This function has the two nested for each loops. Inside the inner loop, it converts a grid location into a flat index. And it then generates a hexagon at that location. The complete grid of hexagons is created by calling the fill function 2 times. The second time, the hexagons are offset, 2 positions in the x direction, and 1 position in the y direction. This will ensure that the 2 sets of hexagons will interlock. The hexagons generated in the previous slides are irregular hexagons. The edge lengths and the angles are not constant. Sometimes, it may be necessary to generate a grid of regular hexagons. The images show 2 examples of packed hexagons. The top one is packed with irregular hexagons. The bottom one is packed with regular hexagons. We will assume that we are creating regular horizontal hexagons. For the regular hexagon grid, the hexagons need to be 4 grids wide and 2 grids high. In the diagram, we are calculating the horizontal spacing of the grid cells. We define the length of each hexagon edge to be 2 times x. Using trigonometry, we can calculate the horizontal spacing between grid positions. The horizontal spacing will be 2 times x times cos 60. This simplifies to x. So this means that in the horizontal direction, the grid positions can all be spaced by the same distance. We can also use trigonometry to calculating the spacing in the vertical direction. In this case, the spacing will be 2 times x times sin 60. This simplifies to x times square root of 3. The process of generating the grid of points can be broken down into a series of simple calculations. First, we specify how many hexagons we want in the x and y directions. Then we calculate the number of positions required for those hexagons. Then we specify the spacing between the grid positions. In the x direction, we set the spacing to be 10. This means that the hexagons will have edges that are 20 units long. In the y direction, we calculate the spacing based on the previous formula. In the screen capture, the line of code that calculates this is highlighted. Based on the number of positions and spacing, we then calculate the overall size of the grid, in x and y directions. Finally, we generate a grid of positions. Now, when we generate hexagons on this grid, they will be regular hexagons. We have demonstrated how a pattern of close-packed hexagons can be generated. The same logic can be applied to generate many different kinds of patterns. Here we show a pattern consisting of squares and octagons. Finally, we also show an example of a grid that is not planar. In previous examples, we kept the grid of positions on the xy plane. However, this is not a necessity. The grid of positions can form any type of spatial pattern.